Good morning, everybody, and welcome to today's Celsius Talk. My name is Sarah Johnstone, and I'll be moderating today's webinar, where we'll explore the topic of optimizing district heating systems by looking at the cutting-edge innovations of the OPTi project. OPTi has been making waves with their forward-thinking approach to this important issue, and we are honored to have them as a Celsius City supporter. We have just been discussing how OPTi has really shown how district heating technology doesn't have to be something old-fashioned, but can really be leading the edge in energy systems innovations. In this webinar, we have the privilege of hearing from three presenters. Wolfgang Birk will introduce us to the project, and then Yvonne Ritter will present OPTi's work on system virtualization. And we'll then hear from Wolfgang again on OPTi's approach to control and their virtual knob innovation. Finally, George Thanos will take the floor and present OPTi's work on automated demand response. So let's move straight on to the first presentation. Wolfgang Birk is Professor of Automated Control and Vice Director of the Area of Excellence Intelligent Industrial Processes at Luleå University of Technology. He holds an MSc degree in Electrical Engineering and a PhD in Automatic Control. And he's currently coordinator of the OPTi project, which is funded by the European Commission within the Horizon 2020 framework program. Wolfgang, the floor is yours.
Thank you, Sarah, for introducing me. I will give a short introduction of the OPTi project. I will just start with a number of quick facts. OPTi started in March 2015. It's a 32 months long project and has a grant amount of 2.1 million euros. Important to note is we have two pilot sites, one which is in far north of Sweden, and Luleå Energy is the provider of that, and the other one is Sampol, which is an energy company on Mallorca. So very different climatic conditions for those two pilot sites. The project is coordinated by me and also assisted by Arne Jylling, who is working on this, and you can contact us on a number of different channels. Most importantly to note is we have some targets in the project, which is 5 to 10% less energy consumed, 40% less peak loads, and important technologies that we develop is, for example, the validated virtual twin. We want to widen the comfort zone of the users, or the consumers in this case, and also increase economic benefit. Let's go back. What is the background here? I just take the example of Luleå here from the start. You see Luleå as the circle there in the middle. So it's close to the Arctic Circle, so we have quite particular climatic conditions. There's a medium-sized district heating network, which you can see on the right-hand side here now, and the blue lines are essentially the largest supply lines for the heat. On the bottom you see the main CHP plant, which is a plant that is supplied by surplus gas from a steel mill, which is able to more or less heat the complete city of Luleå. In a little bit from the complexity perspective, seeing we have more than 46,000 pipes, 800 kilometers of total pipe length, and more than 9,000 buildings which are supplied by that. So if we look at that more in detail, we can say, well, heating is required when, of course, the temperatures become low. So seeing here that the temperature at one point is actually going down to below minus 30 degrees, obviously we can expect that there is a demand rising. So the load in the net is increasing. We see the peak, which is then on the top, and which is then the requested load. As a response to that, we will, of course, supply more heat to the network. On the right-hand side, the supply is the CHP plant that is supplied by the mill, and the other ones are the auxiliary plants that also need to kick in when there's not sufficient supply. But this was then the top level in a sense. When we look a little bit further down, we can see that this renders supply temperatures, and these supply temperatures in essence lead to that pumping is increasing and flows are occurring, and you get differential pressures which are at different points in the network. And furthermore, we want to have a relatively low return temperature, which is good for a CHP plant if it wants to create or generate electricity, for example. So all this binds together. But on a low level now, when we see that, there are some things missing actually. For example, we always see that the control system is not there. Nobody is usually talking about the control system. We are always assuming the control system is properly designed, working well, and tuned also well. But that is honestly not really always true. So control systems are often designed once and then they are changed very rarely or not at all. And very often you have controllers that are actually remaining on default settings as they have been installed, which is usually a problematic situation. So you will render oscillations, variabilities in the network that are preventing you from having an efficient transmission of energy. And so in that context, we can think back that, well, control strategy, is it really optimal? We can wonder if the controllers are actually adequate. Do we use the right type of controllers? Are they connected with the right sensing information? And also, are the components that we use, are they adequate? Do we have right sizing of valves, for example? And in the end, we also want to know, is the heat and cold that we would supply, is that really the demand that we need to supply, or could it be less, for example? So these are questions that we should keep in mind now. And Opti is dealing with those questions essentially. And our thought, how we address it, is by looking at this little sketch in the bottom. You can see there is the virtualized physical infrastructure. Essentially, we create a virtual twin of the real-life system and representing it in a virtual computerized environment. And using that kind of environment, we can then design control optimization methods, assess economy. We can also assess the system and its feasibility, if all components are correct, and we can do that in a virtualized environment. And then when all these assessments are done, we can actually roll it out into real life. So this is the Opti approach to it. And we can also think of how we can involve users, which we will do, and also bring in a gender perspective in the whole development process. So this is a little bit what Opti essentially is about. And here's also a short view on the consortium that is participating in this. I already mentioned the pilot plants, and then we have IBM in India, which is an energy center. We have Optimisation, which is a consultancy company focusing on simulation technologies and modeling. We have RWTH as participating part that is working with the data management platforms, which are on the bottom of it. And then we have also TWT, which is working with the virtualization. We will hear about that later. And also AUB, working with the ADR and incentive mechanisms. So this was a short introduction to Opti now.
Thank you very much for that great introduction to the project, Wolfgang. I'm very excited to go now into some more depth and detail about your project, so please let me introduce our next speaker. We have Yvonne Ritter. Now, Yvonne has a PhD in materials modeling and has been working since 2012 as a research manager at TWT Science and Innovation in Stuttgart, where she manages research projects and innovation. In the Opti project, she is the leader of Work Package 2, which focuses on user-centric design, architecture, and KPIs, and she's also the coordinator of the Opti exploitation team. So please, Yvonne, tell us a little bit more about how Opti works with virtualization of district heating systems.
Thank you, Sarah. So Wolfgang has already mentioned why we want to have a virtual twin of our district heating system. So our objective is twofold. So first of all, For new DHT systems, we want to support the design and validation phase. And on the other hand, we want to improve existing district heating systems. For example, test new control and operation schemes, run tests before we replace components, and with all these methods, improve energy efficiency. A district heating network is a rather big and complex system. Here you can see the example of the Luleå network. Wolfgang has already shown it before. We have more than 45,000 pipes, summing up to 800 kilometers of total pipe length. We have more than 9,000 buildings and 5 different production sites in the network. So the question is, how can we model such a complex system? And can we develop a flexible and transferable workflow and tools to create such a model system so that we are not only valuable for our tests and pilot sites, but that we have something that can be transferred to any district heating network? And for this, we try to start rather simple. District heating system can be described as a simple network. The network has a number of nodes. First of all, we have here the consumers in the different buildings. These are the sinks of our network. And then we also have sources in the network, which are production sites. And these nodes of the network are connected by pipes. And this is a very simple illustration of what a district heating network is. For sure, you have a lot of other components like a number of valves and pumps and whatever, but now I will focus on these main components here. Now the question is, how can we model these individual parts of the network? And which data do we have as input actually? So first of all, let's take a look at how we model the consumers of the network. In Opti, we use 2 different approaches for this. First of all, we have the black box modeling approach. Here, the consumption is estimated from plain time series, actually from historical data, using data analytics techniques, in our case, machine learning. And we don't consider physics at all for these kind of models. What we get out from the model is consumption of hot water and heating. So just one parameter. To get a better basis, a better data basis for these models, what we do is we group buildings into different categories and develop one black box model per category. For example, we have single-family homes, we have multi-family houses, and we have public buildings, which have different consumption characteristics. The other type of models that we produce is gray box models. What we do there is we create more sophisticated models. Here in the bottom you can see a picture of the system that is modeled here actually. So on the left-hand side we have the network, and on the right side the building that we model with different components like the radiators, thermostats, valves, and so on. So we have here a combination of data analytics and physics to represent a building. The buildings are modeled using principles from thermodynamics and heat transfer, and the parameters that we need for these models are estimated using historical sensor data. What we get out from the model are various parameters, for example, indoor temperatures, water return temperatures, mass flow rates, and so on. So this is really a more sophisticated approach, and we get a lot more information out of the model. These modeling approaches are main Opti project outcomes, and we call these outcomes Opti asset. And every time I talk about an Opti asset in my presentation, I have this green logo. So you always know that there's something behind it. So now we have covered the consumers. How about the pipes? Starting point for the generation of the network model are the coordinates and dimensions of all components in the network. And these we get from Geographic Information Systems, GIS. The advantage of this approach is that if we base our modeling on raw GIS data, we will always have an up-to-date model that really reflects reality. But as you've seen before, the network is very, very complex and large. So we really have a need to reduce and simplify the network, and we will also not be able to manually generate a model for such a big system. So what we do is we start with the raw geodata, and then we run reduction and simplification algorithms. The reduction is done based on, for example, pipe size, customer category, and also the use case that we want to take a look at. And then we simplify the system by applying network analysis algorithms. And in the last step, we have algorithms for automated model generation, and we end up with a virtual model of our network. This approach enables simple updates of the model. So whenever changes in the network occur, we can run this tool again and end up with a very up-to-date model in the end. And this, again, is one of our important OPTi assets, this tool. So now we have the consumers and the network. But what I've said now in the context of the simplification is that we use the use cases as a basis to simplify our models. This is a very big advantage of the OPTi approach. I will show you two examples. So we have one example use case here, decreased supply temperature. At temperatures well below zero, the temperature which is supplied to the network is chosen using a linear relationship between the outdoor temperature and the temperature that is supplied to the network. And one goal of OPTi is to optimize this curve and reduce the supply temperature in order to save energy. This use case now requires that the energy demand of each consumer in the network is satisfied at all times, and that's it. And for this, a black box building model is sufficient to investigate that use case. So we can prepare the network model accordingly. The second example, peak load reduction. Peak loads occur, for example, in winter times when in the morning when a lot of people take hot showers and all heatings are turned on. Then we have a very high energy demand, and this means that auxiliary boilers need to be switched on in the network, which is economically not very attractive. So if this can be prevented, for example, by preheating and then switching off the heating during the peak hours, we can really save energy, save money, first of all. And this use case requires now to assess the indoor temperature together with the impact on energy demand. So we need more sophisticated models, which we get from the gray box modeling approach. This tailoring of models based on the use cases ensures, on the one hand, that we have sufficient simulation performance, and on the other hand, that this approach is very flexible. To integrate all the models into a virtual twin, we use a co-simulation approach. Here, a co-simulation master connects all the different models and controls the signal exchange between the models. Our co-simulation master complies with the FMI standard, and that means that the interfaces to the different models is standardized, and therefore we can really integrate a lot of different simulation tools here. This approach secures flexibility and reusability. One important aspect that I've not talked about is the control system model. As Wolfgang already mentioned in his introduction, that is something that is very important for OPTi and really an integral part of a district heating system. But he, as an expert, will talk about this in his presentation. this virtual twin of the district heating network is what we call OPTi-Sim, and this is a very important OPTi asset. And here you can see the result, or one result. This is a visualization of the virtual Luleå network here. And yeah, this graphical user interface is something that we're still working on right now. So in summary, OPTi has developed a flexible and transferable workflow for creating a virtual district heating system, including consumer modeling approaches with different complexity, a tool for automated network model generation and simplification, and an FMI-compliant co-simulation that integrates all the components of the district heating system. The workflow and tools have been applied for the Luleå district heating system, and right now we are working on validation and first tests. Thank you for listening, and I'm happy to answer some questions.
Thank you very much for that presentation, Yvonne. A couple of questions spring to mind. One of the strengths of your modeling work is how comprehensively you model a lot of different aspects. And you had a lot of different green diamonds there signifying various different assets that your modeling work has produced. So my question is, at the end of the project, will there be some kind of integrated tool where we can put together all of these different assets that you've shown us in your presentation?
And so this is exactly what we will not do, one integrated tool. Our idea is that we want a flexible approach at the end of the OPTi project with different assets that can be combined according to what an individual district heating provider needs. So we have different tools, different algorithms, different workflows that we provide together with some guidelines. And this, in the end, will be a very flexible toolbox where, different users will be able to find their individual solution. So this is our idea behind OPTi.
Oh, that's fantastic, because if there's one thing that we've learned from Celsius, it's that even if there are a lot of similarities and challenges and solutions, that tailored solutions are really the ones that are best. Everyone has different needs. So I think this sounds like a very sensible approach to have this toolbox of different models. Another question I have as well is, when you're presenting, for example, the Luleå district heating network, you said you were modeling the actual network as over 40,000 pipes. When you're making your kind of simplified models, how well does the model correspond to the real network? And what implications does this have for your modeling?
Yeah, so actually our goal is that we really represent what's going on in the real world very well, because only then, for example, the utility company will rely on the results that it gets from the solution. And this is what we are working on right now, this validation, and we are working closely together with Luleå Energy here. So they provide us with the historical data that we can validate our simulations against, and so far it really looks very good. I cannot tell you numbers, to be honest, at this point, but our goal is that the engineers from Luleå Energy say, okay, yes, for me the virtual twin represents the real world, and I can rely on that. So this is our approach here. We have a number of what we call events that we have defined. They were defined by Luleå Energy, and we try to simulate them with our simulator, and they will compare the results and give us a thumbs up or down in the end.
Okay, well, we will definitely look forward to seeing the project's final results, but thank you very much for this presentation in the meantime. Very exciting work. We'll hand the floor now back over to Wolfgang, who will take us further into the control side of the project. But first, I can just add a few more details about Wolfgang's extensive background. He's worked for many years with development of active safety systems and process control application for resource-efficient processes. And he's done that in a lot of different areas. In fact, for example, he received the Henry Ford Technology Award in 2007 for working with Volvo Cars Driver Alert. But I'm sure I can speak for everybody listening here today that we're very happy that your focuses are at present on district heating energy systems. But his main research interests are the application of estimation theory, control structure, and configuration selection in large-scale systems. And the main application areas are intelligent transport systems, process control systems, and energy systems. So with this wealth of experience, there's no one better to present the next part of OPTi's innovations. Take it away, Wolfgang. The floor is yours.
Thank you, Sarah. I will just go back to the questions that I was asking in the beginning when we talk about control. And one important thing is, as Yvonne also mentioned, is we actually rarely see the control system anywhere. And also in the simulator, it's similarly that having the controller as part of the simulation actually gives us a very good understanding on how the real-life system is working, and also how it will act when we make changes in operating conditions, like we move from one supplied heat amount to another. Then we can see the transition from one level to the other, and that might not be so smooth as we would expect it in all cases. So going back to these questions, I always like to ask this is, again, control strategy optimal? Do we have adequate controllers? And also, do we really need to supply the heat and cold that we think we need to supply? So let's go into the optimization side here. We have chosen a fairly classical idea about building a hierarchy when it comes to control and optimization. This is fairly established since many years, where we actually say that, well, we have the low level, which is directly connected to pumps, valves, and production units, where we essentially directly control these actuators in the field. That also means that we somehow have to build these kind of connections where we say, well, I measure at some point and then I actuate at another. And this question is quite critical in achieving good performance. When we have achieved this low-level control and it's working nicely, then we can essentially adjust set points to the low level. So we build a hierarchy. And on that higher level, we can use optimization-based control schemes. One of the most well-known is, of course, the model predictive control scheme in that case. And when we take it another step up, we can actually say we would optimize operation, which is once again also types of set points that we adjust for the lower level, but they integrate much more the scheduling side, how do we run production, and also how are users consuming energy. I will bring a little bit more details on this. When we see at this picture, again, we can say on the top, we see a number of phenomena that are affecting the district heating cooling system. And on the bottom, I summarize a number of different kinds of methods or technologies that could be used. So it's very clear that environmental factors like weather and temperatures, they are affecting largely the operation of a system and also how it should be controlled. Then we have the market, consumers, and also the demands, where there's a connection between the demands and the environmental factors, especially thinking of the temperatures in the field. So we can say that these are affecting how we would want to control. And the lower levels, they should just follow what we decide on the higher level, of course, because in the end it's us, the humans in the buildings, that want to actually have a comfort. And in that sense, we want to supply everybody with the energy that they actually need. So if we look now on the bottom up again, then we can say we have the low-level controllers, and what is very often used is essentially PID type controllers. So this very old technology in a sense, which comes from already in the beginning of the 19th century, but it's very much technology that is proven, it's easy to use, and it has a high level of versatility. Another thing when we come to this aspect is that in some cases you have then these kind of controllers, and they are only measuring at one point and actuate at another. So when you do that, you can ask yourself, which are these connections? And then we talk about a problem called control configuration selection, where you actually need to select how these combinations are. And I will bring a little bit more details on that in my next slides. And then on the upper level, we build predictive controllers, and I can also show you later something about how to facilitate the design of a model predictive controller that can be used in a real-life setting. And then we have the ADR and the supply curve optimization, and George will tell us also later about ADR a bit more. So I go on now to the control strategies actually. So when is a control strategy now optimal? So we can see here on the right hand side, it's a prototype tool which is called ProMoVis, which is has been designed essentially for the pulp and paper industry in the beginning, but has been used a lot in any other context of process control as well. An energy system like district heating system is also very similar to a process control system. And in that way, we want to know what kind of connections do we actually need to control. In the picture there, we can see the red nodes, they are the actuators, and we have a number of green nodes. This is a very simplified model just for this showcase. So on that model, we see there are a number of components in there. These red spiderweb that we see right now are all these connections that are more or less affecting the system. It's more or less the virtual representation, in a sense, how an actuator affects a measurement. And in that sense, we can understand how that is actually occurring. But from that spiderweb, it's really hard to say what kind of connection is important. So the mathematical tools that are actually built into this tool ProMoVis helps us to take these decisions. I've zoomed in now a little area where the green node to the left is a differential pressure, and the differential pressure is actually about supplying a certain flow. Here we can see that there are a number of actuators that have a connection to this green node, and some of them are actually quite white. The whiteness in this case is indicating us the importance or the significance of that actuator for controlling this kind of connection. So in that sense, having this in place, we can validate the current control strategy we have, if we do a good job in actually using controllers in the right way, or how we can actually improve them. And this can be done by these kind of tools that graphically then can represent these kind of important interconnections. And it's important to note that making a wrong choice here limits the achievable performance and often renders oscillations. And oscillations in pressure and in flow, they are actually preventing us from being efficient. So this tool enables us now to take an optimal selection of control strategies, and it is essentially a decision support where an engineer can decide and discuss with people in the field if this is a feasible change in the control strategy. Another thing that we are looking at, which we have discovered, is that substation controllers, they are not very often appropriately tuned. Often you have a controller and then it resides there over a long time. Sometimes you also make changes. You switch a valve or replace it. Valves get worn out. So you should actually do an adaptation of that. In that case, we can also, is it really adequately tuned? And we have developed a tool here which can be used to actually solve this kind of problem, because it's always difficult to know exactly what are you controlling. So this tool has a graphical user interface. You can, from an experimental perspective, load in data, analyze it, see the performance, and then also find a new controller tuning that can, in some cases, of course, simply validate the one that you use, or it can indicate to you that there is an update possible. So it just gives you new parameters to an existing control scheme that you already have. And right now the tuning based on experiment is essentially done. We have experimented with it. We have tested it in a couple of cases. For the component-based modeling, it's not yet completely ready, but it will reduce the experimental burden essentially on the people in the field. Another thing is that I talked about before is optimization-based control. It has become very popular in the latest years that you use a controller which is more or less taking care of what's happening in the future with your plant, but also that it is considering the constraints in your system, because you have limitations how much heat and cold you can actually supply. So in that way, we have this problem of having a very complex control scheme, which is doing a real-time optimization essentially in a closed loop context. And then you can also have, how do we actually design it? So the background here is, of course, that we want to reduce peak loads and we want to consider weather conditions that can be foreseen. And we want to deploy easily these kind of controller schemes. So what we enable here with this user interface that you see to the right is that you simply can choose the different kinds of variables that are of interest for your control problem. It then combines them together in these so-called cost functions that you want to optimize, and you can adjust the different kinds of time horizons for control and prediction, which is adequate for your own district heating system in this case. And as a result, it generates the MPC controller right away. And that can be then used directly in the OPTi-Sim for validation purposes before you actually deploy it in the real field. Last but not least, I want to just show you this so-called virtual knob concept. It's actually about understanding the user. And this is also a component that we easily can bring in to this optimization context and optimized control aspect, where we think of that the user's understanding of comfort is important. So how do we get a live feedback from the users? And in our case, we think of, well, we think of a building. We stop at substation level because we don't look at individual users. We look at the users in that building context. So we built a simplified interface, which is quite known to most of you. It's very often used at airports, for example, when you pass through a security check or something, if it is understood as apprehended as a good or bad. Now you have to see that the interface is in Swedish because it was developed for Luleå Energy at the moment and tested there. So the user can simply say if it is too warm, too cold, or it's just okay. And in this way, we can establish actually something which is called the comfort zone of the people living in that building. And what that actually means is we can establish how much heat and cold is actually needed. This graph on the right-hand side shows you the responses that we get, and it's on the lower side you can more or less see the temperatures that you have and how it's apprehended. So we can by that apprehend what kind of comfort zone is adequate for most people, and then we can use this in the optimization scheme because we introduce a flexibility then where we can say, well, we can actually lower the temperature here a bit, and still people will be okay with this kind of temperature level, and that will of course save a lot of energy. And it also helps us to understand if we can widen the context and how much of complaints could we actually deal with from a energy company or building company perspective. A typical problem here is, of course, the access to data and how it can be shared and used, because integrity and privacy issues, they are important to be considered in this context. Just to summarize, so we have developed, as said before, a number of different kinds of tools, and they can all be used in combination. So they are interoperable, but they are not depending on each other as a full. So we can use them independently and tailor to the different contexts of the DHC systems. We can integrate it with the OPTi-Sim using this FMI standard, and the tools that are most interesting right now is the control configuration selection and tuning of low-level controllers, as well as design method for predictive controllers in this context. And what we are doing now is that we are in the final testing of these tools, and the initial evaluations that we have performed, they show very promising results. So thank you.
Okay, thank you very much for that, Wolfgang. Is it okay if I ask you a couple of questions?
Of course.
Okay, wonderful. Well, we had a lot of very interesting content there, but I was just I enjoyed your presentation of the virtual knob concept as well. And I wonder, when you've been testing and working with these things, have there been any surprising results? You mentioned at the beginning of your presentation the importance of the human element, and in your work with end users here, have there been any surprising results?
Well, especially when it comes to the evaluation of the virtual knob, I think for us it was not even comprehensible to know what is the actual comfort zone. I mean, when we talk about, for example, the Luleå Energy building that we have been investigating here, it was hard to actually put any numbers on that. And by having this kind of feedback, it's actually possible to establish this kind of, let's say, area where we say, well, here we have that the people working in this building, they're actually sufficiently happy with their work environment from a temperature perspective now. So in that sense, this was for us really good news in a sense, and also a surprise that it's possible to establish these kind of zones. And they are really an enabling factor in that sense.
Okay, great. Thank you for that. You also you presented a range of very interesting looking tools and methods. I'm wondering, what is the maturity status of these? Can they be used straight away?
Some of the tools are right now implemented in, let's say, a prototype environment. We use quite a lot, for example, the MATLAB environment right now. But for example, the ProMoVis tool and also the tuning tools, they can be essentially deployed as so-called standalone applications in a sense. They are still prototype tools, but they can be used. And the maturity is, I would say, we work here on a maturity level in this research project until, let's say, 6. So they are all tested in a so-called realistic environment. So they can be used right away with a certain level of caution. I mean, they are not really validated in a large number of tests and different environments, but they can certainly be used, and we will also be happy to support that.
Okay, fantastic. My last question is, you mentioned in fact, in your introduction to this entire webinar, the dangers of only looking at something once and not updating it. So I'm wondering, these tools that you've presented to us now, do they still work even after, say, you updated the OPTi-Sim with new models?
Yeah, yes, that's a very good question. Because the most important thing here is that the models that we use in these tools, like for example, when we design the new MPC controller, they actually work directly with the models that we have from OPTi-Sim. So we extract simplified models for the design of MPC controllers from these systems. An MPC controller, for example, is very dependent on a updated model. So if the model becomes old and is not really in line with the current system, the performance of the MPC controller is also getting worse. So in order to deal with this, we can update OPTi-Sim in an automated fashion. And then when that is updated in automated fashion, we can also extract a new model for the design of the MPC, so we can update also these advanced controllers in a sense easily, because it follows essentially a workflow in this sense. So yes, I very much want to say that these updates of models and the underlying simplified models that we use for these decision-making tools, they are actually also updated then in an automated fashion.
Okay, thank you very much for that answer, Wolfgang. And now, without further ado, we will move along to our last speaker for this webinar. George Thanos is the Research and Innovation Manager in the Technology Economics Lab of the Athens University of Economics and Business. He holds a PhD in Technology Economics, Masters of Science in Telecommunications, and also engineering qualification in computer systems engineering. He conducts multidisciplinary research in economic and business modeling, analysis and optimization of new technologies in the areas of energy, ICT, and telecommunications. He also has a wealth of experience of technical and management positions in multinational research and development projects. And in OPTi, he is the leader of Work Package 3, Consumer Modeling and Incentives, and he also is the leader of Business Modeling work in Work Package 7. So the floor is yours, George.
Thank you, Sarah. So I'll just try to give you an overview of the work that we are doing in OPTi regarding demand response. So to start with, what is demand response programs? They are programs that we use a utility can use to reduce energy demand peaks. So they are used basically to address supply and demand imbalances. There's just one way to do that. However, in order to do that, in order for people to reduce consumption, first of all they need to know why to do that, and this is where we come as OPTi in that sense. For example, I'll give you a real scenario from our OPTi pilot in Luleå. During specific peak hours, the Luleå Energy, the provider there, has to activate a very costly and not efficient for the environment also backup production plant, a peak load generation, to meet the demand that cannot be met by the main boiler used. So what we would like to do in that case is we would like to see how we can employ DR to avoid the activation of this backup plant. The major challenges is, first of all, as I mentioned, we need to know how much it needs to be curtailed. We need to know how can we incentivize the user in order to do that. What shall we give them? Is that money? Is that something else? we need, of course, when we are talking about contract with a utility, to insert this in the contract to be one part of the contract. This will help us to automate the whole DR process. So if we think of the future, there are also studies that shown that consumers don't want to be involved a lot in the DR process. They don't want to be asked to do things. They want things to become a reality in a more automatic way. So it's as we say, we don't want to be very intrusive when we're talking about an average user or a family in an apartment, for example. The industrial case is something different that we will not address here. So what OPTi has contributed in this area? First of all, we have defined a methodology for designing efficient contract-based ADR programs that take into account the consumer preferences, as well as the external context, for example, the weather. Consumers are compensated for the amount of energy that we ask them to reduce, and we assign also an optimal schedule having as a target to maximize their net benefit. We're talking about net benefit. We are here dealing with some basic microeconomic concepts. So we are talking about maximizing the utility of the consumer and deducting the payment out of that. When we're talking about utility, this comes back also to the nice discussion with Wolfgang before on the comfort of the zone. A basic let's say term that we use, the comfort modeling in project. When we're talking about TR, we deal it as following. We assume that you as a user, you have a baseline consumption. For example, we have analyzed your consumption and we see that every Wednesday afternoon you would like to watch your favorite Champions League match. Maybe this does not apply to you, Sarah, but men have a very big utility, a very big satisfaction, let's say, that comes out of watching their favorite team. Now, if you ask them to do something, at that point, for example, turn off the TV, if I use a very simplistic example, that means that the user has to reduce his utility quite a lot. And then to do that, of course, he has to be compensated also quite a lot. You have to convince him to do that. So what we are doing in OPTi, we have modeled the comfort of the user based on the consumption. So we know, we have analyzed the different buildings based on real data, and we know how much they consume, also take into account specific weather conditions. We use some statistics models for that, and then we try to send them, as we'll explain a bit later, specific DR incentives that are customized for the specific building or user depending on the context. We have tried to use some very innovative behavioral aspects, like exploiting the altruism of the users. This is some research that we have done later on in the project. It's important to mention that we have evaluated such DR mechanisms both in the smart grid sector, but also specifically for district heating networks. I am saying that because if you try to look up, let's say, demand response programs in literature in real life, you will realize that all of them are applied in the smart grid and the electricity networks. So it's a more traditional electricity network. But in OPTi, and this is what one of our innovative aspects is, we investigate how this can be explicitly applied and exploited for district heating networks. One of the outcomes of the project, an asset, as Yvonne said before, that we would like to bring out to the community, is an ADR tool that we have developed for DR designers. This is a prototype that it is mainly developed for research purposes, but it can also be used as a proof of concept, and also used for later on for building on that and implementing some additional algorithms. what is that tool now? If you can see in the picture, we have in this high-level architecture two different modules. First of all is the consumer baseline estimation module. As I explained before, it is of crucial importance for us to understand the baseline of the user, what the user consumes, and what is the utility that gets out of using, for example, the inside temperature of the house, how much happy is from having 22 degrees, and how much not happy will become if this will be changed to 20 degrees. In order to do that, we need to analyze the consumption of the user, and we extract the baseline of the specific user or building, as we have tried this in the Luleå pilot context in different buildings. Then we have some ADR algorithms that use these predictions of the baseline estimation module, and based on a specific set of objectives for the ADR event, for example, when this ADR event will take place, selects the optimal set of users or suggests to the provider an optimal set of users to be targeted, and more specifically, we also provide a suggestion on the amount of incentives that can be offered for the user in order to provide this change of his energy behavior. We can also provide, if asked, a schedule for the whole day. For example, in different time slots, we can suggest that the user A should use his devices, or in the DC concept should have this, for example, temperature inside the house at 10 o'clock, and then at after 2 hours we can suggest that this should be changed up to 0.5 degrees Celsius. So the output of the tool is a suggestion, as I said, for the provider on what type of incentives to use for what specific set of users, in order to have the highest probability, because you can never, of course, be certain that the user will do what asked, so that this can be sent as a DR signal, for example, via monitor of the user, or if you are talking about a more futuristic system, in an automated way, this can be used as a term of the contract, and all this operation will take place in a more automated fashion, so the user will not intervene at all. Would like also to show you a screenshot of the tool that you can see. This is a tool based on runs on a MATLAB core machine, and uses also a Java-based interface. You can see that the provider can select what type of algorithm or policies can be used in order for making the calculations, and having as a result, as you can see on the right hand picture, the result of what are the suggested customers to be used for the specific type of event that will take place, for example, on a Monday morning on October. We have these algorithms have also been disseminated in a number of conferences, so if you can have a look on the right hand side, you can find more details. If you're interested more on the scientific perspective of that, you will find quite a lot of information on how these algorithms are developed, and what is exactly the theory behind all that. So, to summarize, we have evaluated these algorithms in a simulation environment using real data from our OPTi pilots. We have shown that under specific settings, when we're saying settings and assumptions in this case, for example, specific data sets, specific price of that the consumers are charged, different specific type of buildings with, for example, when you're talking about the pilots, we have buildings with 7 or 8 apartments. We have tried also in a more complex simulation environment to target specific apartments, so there are different settings. And we have shown that in many cases we can achieve a reduction of peak demand by 20%, and limiting the comfort of the consumers by only 10% comparing to their baseline case. And this will happen while compensating them with a relatively low total amount of incentive. Now, what are the 3 key challenges to be met in order to have a DHC ADR-enabled network in the near future? It is important, I said, that we will try to automate the DR. To do that, we need certain devices like remote controlling of thermostats or the supply temperature at the user's end. We need to elicit consumer feedback in a non-intrusive way. As Wolfgang presented before, we have the virtual knob. So it is one thing having the estimations of the models, and it's another thing having also the real input of the users. What we are doing in OPTi is we try to combine this and retune and make our models better by having actual information feedback from the users. Another key challenge is what type of incentives to use. There is a huge discussion in the last 20-30 years from researchers whether people should be incentivized with real amounts of money, or they can be given some behavioral triggers, especially as we've seen in the energy efficiency case. For example, to say that the users, you should do that because you're now saving one small green tree. And simple things like that sometimes we have found that work sufficiently well compared to price-based schemes and with less intrusive technology and less effort from the provider. But this is a big discussion, and it comes down to the specific environment and the target that the provider has in for his network. So as a result, OPTi will provide a set of suggestions for stakeholders that they can take into account and consider if they want to implement DR algorithms in their networks. So that's it from my side. I'm happy to share any questions that you might have.
Okay, thank you very much for that presentation, George. I do have a couple of questions. You talked at the end of your presentation, you sort of made a nice summary about some of the ways that you can target end users and provide incentives for them. I'm wondering, is there an economic justification from the energy provider side for working with these kinds of systems?
Yeah, this is a very important question that we have came across quite a lot of times. So the question is simply, what is it for me if I am a provider? First of all, we have to look at the specific case. For example, we know that even a very small peak reduction will actually have, in many cases, a very big economic effect on the provider's side. How much that is, someone should know the explicit, the detailed economic analysis, financial details from a specific provider. Then there is also the question, how much of those are you willing, for example, if avoiding a peak plant will save you 100 users, how much you as a provider are willing of that to give back to the users as an incentive? Is it 10, 20? This is up to you to decide as a provider. Of course, the more you give, the models will give you better results. What in OPTi we are doing is, in order to also have a complete full case as a proposal for stakeholders, we're doing a specific cost-benefit analysis based on standard financial modeling techniques, And for the OPTi, in particular for the OPTi Luleå pilot, we are working together with the provider in order to estimate these financial seats, and at the end to see whether there is internal rate of return or return of investment for them to implement such solutions, and what also a type of sensitivity analysis on what are the factors that are influencing that. So this is something that we will also provide as an asset, this specific financial modeling paradigm. This is something that OPTi will provide as an asset at the end of the project.
Okay, thank you very much for that answer. I have another question more related to the other side of the equation, the end users. In demand response initiatives like the ones you're working on, is there a value in informing end users of a system perspective? How to operate the city's heat supply most efficiently? You talked about other kind of more sort of me-focused incentives for end users, but do you think there is any value in terms of trying to bring a system perspective to the end users?
Well, it comes down on what your users are. Because we are talking here about energy networks, the traditional, let's say, networks, in the traditional networks, users are not, let's say, educated in doing such interventions in their systems. So it is something that experience has shown that we would like to be avoided. There is a huge amount of work that is currently being done, for example, on how to educate users via gamification approach in order to actually provide the same results without having the user to change their system settings. So experience from my perspective and based on the state of the art shows that users, it is more efficient most of the times that you educate users to do that, and you, in a way, you put them out of the direct loop when it comes to intervening with real systems.
Okay, thank you for that insight. Before we finish off today, I have a few questions that I'll just address to all of our speakers that we've heard of today. So feel free, any of you, to answer. But seeing as you are all from the same project, maybe you will agree with each other's answers. Not everybody has to answer, but anyone that wants to may do so. We've heard a lot of really fantastic, cutting-edge, innovative tools that you have been working on in the project, but you haven't finished the project yet, and I have been hearing a certain kind of like, this is what we have so far, more will come, but that you will also need some more testing. So I have a few questions kind of related to the future of your innovations, but I also have heard a lot about sort of tailored solutions and how things work in different contexts. And my first question is, what have you learned from having pilots in two such different sites as Luleå and Sample?
Okay, maybe I can answer that, if that's okay.
Yes, thank you, Wolfgang.
Well, the difference is, first of all, the size of things. I mean, you can say sometimes the devil is in the detail, and sometimes it's really in the large issues. So just from the Sample side and from the Luleå Energy side, I mean, they are very, very different plants. They have different requirements on them. So, for example, just looking at this control configuration problem, it is very different, both in size, but also in the questions that need to be answered. So it helped us to span essentially the envelope a little bit to see the applicability of our things. And I think that is what is really helpful from having these very different sites. One example is that In the Luleå case, we get very large-scale models. Just to mention a figure, we have a system which has more than 6,000 interconnections, and this is fairly large scale. While in the sample case, it is much smaller, but parts of that network are not well known in the same way as they are known in Luleå. So they have different aspects that we need to deal with simply.
Okay, very interesting. Thank you. Yeah, it must be a real privilege being able to work with two such different sites. So my next question is then about the future, about validation in different contexts. I've heard you say today. I've heard some of these could be used today, but some of them maybe need some more refining or more testing, more validation. So I'm wondering, what are the next steps, and in what ways are these tools that you've produced in the project available for the district heating and cooling community? What can we use now? What will we be able to use at the end of the project, and what still will need external actors' input in order for it to be available for implementation? So sorry, kind of like three different questions there rolled into one.
Perhaps I can start and Wolfgang can jump in at some point.
Yes.
So this is the phase that we are in right now. So thinking about the exploitation of our assets. Yeah, there are definitely some tools, I would say, especially some of the tools that Wolfgang has talked about, that are perhaps available already, but he can say more about that. And then there are some tools like OPTi-Sim and the different modeling tools that will not, where the making available will not be as easy. And there we are right now targeting different stakeholders, companies that already sell simulation tools in this field, and we are basically looking for ways how we can make products out of our assets. This will definitely happen at the end of the project, but we want at the end of the project to know which channels are feasible and how can we integrate the efforts by the different partners, which is not so easy. What will definitely be there at the end of the project is the guidelines how to use these different tools. But with the tools themselves, I think some work needs to be done, and it's definitely related to companies that are willing to take up our ideas and concepts and make products out of them.
Fantastic. Wolfgang and George, did you have anything to add to that?
I could maybe add something to this. For example, I very much agree with, first of all, with Yvonne, that we really need stakeholders in there that represent essentially in the end one unit or one entity that is selling, for example, the OPTi-Sim or any other tool, because we are a consortium combined of many partners, and somehow, I mean, an energy company doesn't want to interact with all of us simultaneously, so there need to be someone that is fronting these products, and so that is an important aspect on this, I guess. At least this is what we have also understood from just from the partnership that Luleå Energy, of course, wants, for example, use the OPTi-Sim even after the project's end, but there would be a need of one partner that is fronting this. One important aspect, if we look, for example, at the ProMoVis tool, is that this is a tool which is an open source solution in the end. So it is freely available already right now, and it is used by a number of companies and also research institutes. So In that sense, it will have a further development, and everybody can essentially use it in a sense as is. But there's also a company that can provide support on the use of it, which is underlying or managing the rights for this open source tool. So the development that we have done here is essentially already more or less available then. When it comes to this tuning tool, for example, we are discussing right now with a number of through Luleå Energy building companies that found this quite interesting as a way of making their life in their normal daily work easier. So there's also an interest to bring this onto the market. And we are really happy to engage and see how this can be marketed as a product. So there's also a large interest in this to actually package it in a way.
Okay, and what about the demand response side of things? George, you said that no one's really been looking at this in terms of applications for district heating and cooling, if I understood you correctly. So how ready are we to start applying this to that industry?
Well, I will just like to add something that actually applies to more assets as well as we see it in OPTi.
Sure.
Our work is a bit holistic in a way that when we would like to approach stakeholders, it's one thing providing an idea, prototype solution, but also in OPTi we currently have been investigated on different business models. So coming back and having the whole loop, both the technological and the business, in order to convince the stakeholders that there is a value added out of these solutions. And it is, as we have seen also in practice, it might be, of course, a core research project, but the distance between research and the real market is quite long. Of course, we cannot promise that assets will be available for the market if you would like to adopt them. But on the other hand, we focus on our proposal in terms of what are the benefits, the technological and the economic business benefits out of this, in order to give you all the information that you need in order to decide whether this is something that can be applied in your company, in your specific business case. This is something that applies in most of the assets, as I see it.
Fantastic. Thank you for that. It's great to hear that a lot of these things are already usable. Some of them will be more usable soon, and then hopefully you will get this further help that you need to really use everything that you've created in this project, because I think it all sounds fantastic. I have one last general question as well for any or all of you. And that is, Wolfgang, you mentioned in your introductory presentation that you also try to bring a gender perspective to the project. I was wondering if you or one of the other speakers could tell us a little bit more about how that figures in.
Well, Yvonne can probably also fill in on that, but I can make a little start. Gender perspective, we have a gender researcher connected to the OPTi project. It's Paula, and she has been working in a project called Genovate, where they have designed and developed a gender mainstreaming toolbox, which essentially aims at facilitating, let's say, innovation. But considering in the innovation process also the gender, and also being inclusive. So the way of how we, for example, actually interact within the project, how we actually look at our results and how we create them such that nobody feels excluded, essentially. And so we had her as a partner in the project that was essentially evaluating us all the time in the way how we act, how we work, how we describe our things. Maybe Yvonne, you could also bring some perspective.
Definitely. So what was very valuable for me was that, first of all, this gender perspective was always present right from the beginning, and this inclusiveness is also a very important aspect, because I mean, this is a research project and we have, I think, 3 active female members in our team, I would say, out of perhaps 15, 16 people. And it has, in other projects I've had the experience that sometimes, for example, meetings, web meetings are scheduled in the evenings, late in the afternoons, where people that have to take care about kids, for example, are not able to participate. And this is something that we've discussed about from the beginning and said, okay, for the consortium, it's better if we have meetings, for example, in the morning. And with this agreement, we are inclusive. Everyone can participate in meetings. This is just one small thing. But if you're not aware of the challenges for certain people, then this creates difficulties and excludes people from a team somehow. And also about how to schedule our meetings, the face-to-face meetings, that we never have to travel over weekends, which is kind of family friendly. And these aspects are very important for me, and that really helps to be part of the team and be innovative.
Okay, and has this influenced the results of the projects as well? Beyond just who is able to be part of making and producing them, which is also a very important aspect. But when you're thinking of end users or things like this, does the gender perspective come in as well?
Yes, I think so. Especially we had also discussions when, for example, designing GUIs, that we are honestly all engineers. This is also in a way a way of excluding people that are not engineers. In that sense, we have a potentially a narrow view on our results, and just by having these discussions and bring that up on the table and questioning, it enables us to go a bit beyond what we usually would do. And our hope is that it makes it actually easier for us to connect to stakeholders, and that they feel in a way more that this is in a way more mature in a sense, and it's not just a engineer researcher that has been designing something. It's more maybe a little bit more mature from this perspective, and a bit more thought through in a way.
And one other topic that we've been discussing, but where we've perhaps not really progressed very much, is that you definitely have different comfort zones when you consider female and male consumers. In literature you can read everywhere that females like it a bit warmer than males, and this causes conflicts. And we've been discussing that, and this was also something that we would, or is something that we would like to analyze using the virtual map. But there, what comes into play is the topic of the data security, and so far we have not really resolved that for us. But this is definitely an interesting topic that we have been discussing about.
Okay, thank you for that. I think these are very important and interesting topics, and I think something that is often sort of neglected when we in DHC innovation and research. So I'm very happy to hear you guys talk about it. And in fact, I think there's probably a good note to sum up the entire webinar that we've had today, is that your project really are innovators. You've done fantastic work in addressing and shedding light on invisible problems. Partly then this with gender, but mostly the invisible problem of optimizing control and optimizing the networks. Really showing all of us in the DHC community that we should and can do better, from benefits from end users, but most importantly in terms of energy savings. So I'd like to thank all of our fantastic speakers for their presentations today, and I certainly hope that the project goes well for you, and we'll look forward to hearing more about your results in the future. Thank you very much, and goodbye for now.